Okay, so with that, let me now define an important concept of normal subgroups, which is related to both the notion of subgroups and group homomorphisms. So the definition is, let G be a group. A normal subgroup H of G is a subgroup. So I'm putting an adjective before subgroup. It's normal subgroup. So it first must be subgroup and it must satisfy more conditions. A normal subgroup H of G is a subgroup satisfying the following property. So it is a subgroup that satisfies, given G, small g in G and small h in H, G inverse is in G. Sorry, it's in H. So given an element of the group and an element of the subgroup, I must have that G inverse. So the group element times the subgroup element times the inverse of the group element must again be an element of H. Okay, so this is what we call a normal subgroup. So in immediate example, if G is abelian, then every subgroup is normal. Okay, this is easy to check because a normal subgroup is a subgroup which has an additional property that if G is in small g is in capital G, small h is in capital H, G inverse is in capital H. The second condition is automatically true in an abelian group, because if G inverse in an abelian group, we can multiply in any order. This is same as G inverse H. So I can interchange H G inverse is G inverse H. Okay. So now G inverse H is nothing but H. Remember that I have to start with H in H, G in G. So I have, because H in H, H is in H, G inverse is in H. Okay. So there is no problem in an abelian group. So normal subgroups really are interesting when you do not have an abelian group. If you have an abelian group, every subgroup is normal. So there is no it's not an interesting new concept. On the other hand, if you have a non-abelian group, you can have subgroups which are not normal. Okay. So for example, take G to be S3. Again, S3, remember, is a set of bijections from a 3-element set to itself. And in my notation, these are F1, F2, F3, F4, F5, F6. If you take the subgroup H to be F1, F2, and I will let you check this. H is a subgroup of G. H is a subgroup of S3 because F1 is identity element and F2 squared is F1. Okay, so, and I'll remind you what is F2. F2 is the function which sends 1 to 2, 2 to 1 and 3 to 3. Okay, so F2 squared is F1, which is the identity function. So it is a subgroup. But H, what do you think? Is H normal? H is not normal in S3. So H is a subgroup consisting of F1 and F2. I want to show H is not normal in S3. So let's take F3. F3, if you recall, is the element which sends 1 to 3, 2 to 2 and 3 to 1. Okay. So let's do, so I'm going to take an element. So remember, a normal subgroup is a subgroup satisfying, take something in the group, something in the subgroup and do this GH inverse, it's in H. So I'm taking something in the group, namely F2, and something in the subgroup, namely F2, something in the group, namely F3, and I want to calculate F3, F2, F3 inverse. But F3 inverse, if you think about it, is just F3, because F3 has order 2. So F3 squared is also F1. So F3 is F3 inverse. So what is F3 composed with F2 composed with F3? So let's just do systematically. Under F3, 1 goes to 3. Under F2, 3 goes to 3. Under F3 now, 1 goes to 1. Right? And where does 2 go? So this is the F3. This is F1 and then F3. 2 goes to 2 under F3, 1 under F2, this is F2. 2 goes to 1 under F2 and 1 goes to 3 under F3. Similarly, 3 goes to 1 under F3, 1 goes to 2 under F2 and 2 goes to 2 under F3. So F3, F2, F3 is the function which sends 1 to 2, 2 to 3 and 3 to 2. Right? And this is not equal to F2. Right? It's not equal to F2. And it is certainly not equal to F1. So F3, F2, F3 inverse is not in H, which recall. So H is not normal. Okay, so it's not a normal subgroup. So Abelian groups, all subgroups of Abelian groups are normal, but non-Abelian groups have non-normal subgroups which are not normal. I want to now introduce two important examples of normal subgroups. Okay, so let's take any group homomorphism. Let's say this is a group homomorphism. Then kernel of phi, which we have already seen is a subgroup of G, is actually a normal subgroup of G. So we already saw kernel phi is a subgroup. To check normality, what do we need to check? So let G be in G and let H be in kernel phi. We want to check that G inverse is in kernel phi, right? What is the meaning of being kernel phi? If you apply phi to it, it must send it to identity. So let's check that. What is phi of GH G inverse? Phi of GH G inverse is, because phi is a group homomorphism, this is phi of G, phi of H, phi of G inverse. Okay, now this is phi of G. What is phi of H? Because H is in the kernel, phi of H is EG prime and phi of G inverse is phi of G whole inverse. So EG prime is the identity element, so this is just phi of G inverse, which is EG prime. So GH G inverse. Okay, so this implies kernel phi is a normal subgroup So kernels are always normal subgroups. So this is an important example of normal subgroup. whenever we encounter a group homomorphism and take its kernel, it's automatically a normal subgroup. A second important example of a normal subgroup is the center of a group. Is always a normal subgroup. So recall what is the center of a group G. It is denoted by ZG. This is all elements G in G such that AG is GA for all. Again, already saw that ZG is a subgroup, right? That's not surprising. That's not new to us. So it's a subgroup. So to check the normality, just like before, we take a group element and a subgroup element, and let's check if what do we want to check? We want to check that GH G inverse is in ZG. What is the meaning of being in ZG? It means that it commutes with everything in the group. So let A be arbitrary. We want to check that GH G inverse commutes with it. So let's write GH G inverse times A. So I'm going to rewrite this as GH G inverse A. Now let's use the property that H is a element of the center. If H is an element of the center, H commutes with everything. So since H is in the center, let me write it here. H is in ZG. H commutes with everything. So in particular, it commutes with G inverse A. Right? So H times G inverse A is G inverse A times H. I'm not disturbing this G. So I'm writing this like this. But now actually, yeah, so I should have been there is no need to do all this, so I'm sorry. So it's much easier than this, because you want to check that GH G inverse in ZG, but because H commutes with everything, so this is G inverse times H, right? H is in the center, so H G inverse is G inverse H. So I'm going to use that. So this is just H, which is taken to be in the center. So if G is in the group, H is in the center, GH G inverse is in the center. Okay, so center is a normal subgroup and kernels are normal subgroups. So these are two very important examples of normal subgroups. Okay, so I will stop this video here. In this video, we have looked at normal subgroups, and we have looked at group isomorphisms. Okay, and this is these are both very important properties, and especially normal subgroups will keep coming up a lot in our course. And in next time I will start talking about cosets of a group and talk about quotient subgroups, quotient groups. Thank you.